In this video, we will talk about transnational viscous damping system. These are the general formula for the system. Cc, critical damping, is equals to this formula, and K is the stiffness, M is the mass. Omega D, damp natural frequency, is equals to this equation, where this symbol is equals to damping ratio, and omega n is the natural frequency, which is equals to 2 pi f, or square root of K over M. Tn, the period, is equals to 1 over frequency, and this equation is the natural energy equation. In terms, x in terms of t, time, is equals to c constant exponential to the power of s t multiplied by t. So mx double dot plus cx dot plus kx equals to 0. By using the root equation formula, we'll get to find two roots, s1 and s2. That will be equals to negative b plus minus b squared minus 4ac over 2a. So here we'll have the plus minus equation, and when we substitute the s1 and s2 into this equation, we'll have c1 and s1 and c2 and s2, which is the root number 1 and root number 2. So assuming critical damping constant equals to 0, we'll have this equation, and by rewriting this equation, we'll have this equation. Next, the damping ratio. So here is the damping ratio equals to damping constant over critical damping constant, and by rewriting the equation, multiply, we'll get this equation. So from this equation, we substitute back into S1 and S2, and here we'll rewrite this equation into this equation, where we substitute this value with this value to get this equation. And there will be three conditions for this system. If the damping ratio is less than 1, it will be underdamped. The damping ratio is equals to 1, it will be critically damped. And if the damping ratio is more than 1, it will be overdamped.
Okay, there are three conditions for a system which are underdamped, critically damped, and overdamped. First, we have to use this formula. Damping ratio equals to damping constant over critical damping constant, where the critical damping constant equals to this formula. The K is spring stiffness and the M is the mass of the system. Then usually the damping constant is provided in the question. Then after that, we can find the damping ratio, and we can know whether it is more than 1, less than 1, or equals to 1. Now we'll discuss the condition where damping ratio is lesser than 1, which the system is in underdamped condition. Now we can try and find a solution xt, or during initial conditions x naught t equals to this formula here, where the x naught is equals to the initial displacement and the derivative of x naught is equals to the initial velocity, and these two are usually given also in the question. And the natural frequency omega n equals to square root of spring stiffness over mass of the system. Also, the spring stiffness and the mass of the system are usually given in the question. And then to find the response of the system, we find x equals to this formula, where c1 prime is the initial displacement, or x naught, and the c2 prime is equals to this formula here, which after we substitute the c1 prime and c2 prime inside this equation, we get x equals to this formula. Then we can find the phase angles, which at initial conditions, the phase angle equals to this formula, And for normal conditions, the phase angle will equals to this formula.
The next cases is critically damped system. This system occur under the condition damping ratio equal to 1 or damping constant equal to critical damping or C over 2m equal to square root k over m. In this case, the roots are S1 equal to S2 equal to negative critical damping equal to m or equal to negative natural frequency. Due to the repeated roots, the equation will be St equal to bracket C1 plus C2 times T bracket exponential power of negative Wn times T. For further explanation of this equation, we can take the initial condition, which is C1 equal to initial displacement, C2 equal to initial velocity plus natural frequency time initial displacement. So we can put this value into the equation to get this formula, which is St equal to bracket natural initial displacement plus bracket initial velocity plus natural frequency is initial displacement close bracket time t and close bracket exponential power of negative Wn t.
Under the overdamped condition, the damping ratio have to be more than 1. After confirming the damping ratio to be more than 1, then you can plug in the general formula for the overdamped system, which is xt equals to C1 exponential to the power of bracket minus damping ratio plus square root of damping ratio square minus 1, close the bracket, natural frequency t plus C2 exponential to the power of bracket minus damping ratio minus square root of damping ratio square minus 1, close the bracket, natural frequency multiply with the t. If the initial condition x0 and velocity is given, you can plug it into the C1 and C2 to get the value of C1 and C2. If the initial condition x0 and x dot naught is not given, then you can leave it C1 and C2 as it is in the xt formula.
Under special condition where damping constant C is not known and the amplitudes x1 and x2 are known, to find the damping ratio, we can use the logarithmic decrement method. To use that, we have to know the general formula for the amplitude, which is x0 to the exponential of negative damping ratio times natural frequency times the time, the whole thing times to the cos of natural damped frequency T1 minus the phase angle. So we use this formula to find the decrement x1 over x2 to the power of this whole thing, and then to find the T2 we use T1 plus the period time, where Td is 2 pi over to the natural damped frequency. So we substitute this formula into the T2 and then we find this. So by this we can just cancel off these two, as these two are the same value. From that we can get this value, and then to find the logarithmic decrement, we just ln x1 over x2, and then we can get this formula, and then from here we can get the damping ratio.